Alright, so the first thing we're going to talk about is we're going to talk about units. And this is going to be a really important thing in your lab reports because you're going to have to use scientific notation and the standard system of units. So we've got in chemistry what's called SI units, and SI stands for Le Système International des Units, so it's a little bit French, but basically these stand for the standard units we use. And once you're in SI units, you can use them together, so you don't have to do any conversions between. So it's very handy to be in SI units. So what are these SI units? Meters, kilograms, seconds, amperes, which is a unit of current, Kelvin, measure of temperature, moles, which is number of atoms, and CD, which is candela, which is to do with luminance, which is kind of like how bright a light bulb is. So I didn't know about that one, so that's quite cool. Now the second thing is scientific notation. Now, thanks to Napoleon, also a Frenchman, we have scientific notation, and actually our number system is also in base 10, which means that we count up to 10 and then repeat. But when you're dealing with incredibly large numbers, you have to use a different system. So what we use is scientific notation to describe very large and also very, very small numbers. So I'm pretty sure you're familiar with this, but I'll just go through it again. So 10 to the 0 is equal to 1. Actually, any number to the power of 0 is 1, which is quite a cool property. And we go up in orders of magnitude of 3. Okay, so this is the equivalent of 1, 2, 3, 3 zeros. That's and the shorthand for that is kilo or K. Now 10 to the 6 is going to be mega. 10 to the 9 is going to be giga, 10 to the 12 is going to be tera. Now you're probably used to this because you get terabytes in your computer. That's the new large hard drive sizes, which I'm sure will get even larger. Interestingly enough, computers don't actually work in a base 10 system, they work in a base 2 system, so everything goes up in orders of 2. So that's why you get 128, 256, 512, 1024. They're all the different orders of 2, and eventually we get up to terabytes. But yeah, it's not actually in base 10. Now let's get small. So 10 to the negative 3 is the equivalent of 0.001. Alright, so this here is milli, so you're probably familiar with that. 10 to the minus 6 is micro. This is a Greek symbol mu. This is Greek, and you'll find a lot of Greek in chemistry, and one of the reasons was that if you were to do sciences, you had to do natural, you had to do kind of philosophy, and part of that was you had to take a language in the first year. So part of the university program was you either took Greek or Latin, and so a lot of physicists and chemists took Greek, and a lot of biology and medical people took Latin. Anyway, a little deviation there. So let's keep going down. 10 to the negative 9, that is nano, that's very, very small. 10 to the negative 12 is pico. 10 to the negative 15 is femto. And this is the pulse width of the lasers that I work with in the lab. So the pulse of light that comes out of our lasers is only about 100 femtoseconds, which is very, 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 very small. And the reason we use this, which is what's called basically a logarithmic scale, is because it helps us to talk about things in basically from 1 to 100 really. and so that we don't have to explain millionths of a billionths of a millionths of a meter when we're talking about, say, a femtometer, but we can actually talk about things much more easily. We can talk about 1 femtosecond or something like that. So we'll find other scales that are used in chemistry that help us to deal with incredibly large numbers. So let's have a bit of a review of some algebra. And the thing that is really important when we're looking at units is exponents. And if we know how to use exponents, we can do all of our unit conversion, everything, using algebra, and we don't need to memorize a whole bunch of conversion formulas which get really, really complicated. So let's have a look at exponents. So we know that if we want to represent x times x times x, we basically write x to the power of 3, and that means basically x times x times x. Now there's a few rules that we have around exponents. If we were to have x squared and x cubed next to each other, that's equivalent to x times x, which is the x squared, and x times x, which is our x cubed. And so in the end we get x to the power of 5. And so this rule is basically xa times xb is going to equal xa plus b. And so that's quite an easy rule. That makes sense. Now let's say we have x cubed over x squared. Now let's write that out. So that's x times x times x divided by x times x. And because we know that that something over itself, so 3 divided by 3 is 1, we can actually cancel out some of these x's. So that x there will cancel with that and give us 1, and this x here will cancel with that x and give us 1 as well, and we're left with x to the power of 1. So practically what this means is that, let's write the rule down, x to the power of a divided by x to the power of b is equal to x a minus b. And something you'll see quite often, and we actually see over here, is that we have 10 to the power of negative 3. So what do you think these negatives mean? Well, another way of writing division is actually by saying it's a negative exponent. So having over here the x to the power of a divided by x to the power of b, I could equivalently write this as x to the power of a times x to the power of negative b. And basically that is the exact same as writing that, because if we use the rule, the first rule we have, it's just x, and I go a plus negative b, which is a minus b. So what this 10 to the power of negative 3 actually means is 1 divided by 10 to the power of 3. And so I'm dividing the number by 1,000 if I have some number over here. And so we can start to think about weird notation which we see, which is, let's just say I've got 3.8. Let's make that a little easier for myself. 3 meters per second. This is also written as 3.0 meters seconds to the power of negative 1, and what that means is that it's divided by seconds. And so that might help you understand that a bit better. And another cool thing about units is that if you memorize the units, you don't actually need to know the formulas. And this is something, you don't need to memorize triangles or anything, you can just purely use the units, which is very, very useful. So let's say I have, meters per second, that's velocity. So velocity is equal to the units meters per second, and so it's meters, which is the distance, and it's divided by seconds, which is the time, and there we go, we've got a formula. We don't need to memorize anything, so that's very, very simple. Another thing is, let's say we've got molar mass, and the units for that is grams moles to the negative 1, which is per moles, or grams divided by moles. And So we can just write that down. Moles is equal to grams, which is mass, divided by moles, which is usually